Good morning. My name's Kevin McDermott, and I'm with Imperas, and we're going to be presenting a tutorial this morning on verification. Within RISC-V, verification is a key topic, and we'd really like to encourage you, as you start your RISC-V projects, to come and listen about verification. So we're really going to be talking about the DV verification, and we'll be covering this slide in a little bit more detail. We really just want to give you that first impression of the collaboration effort that's going on between Imperas, Google Cloud, metrics, and building a verification flow that's available to all under the open source. And our thanks to our sponsors, CHIPS Alliance, Open Hardware, and Low Risk are fully involved in this activity. Now, for some of you that may not have been involved in the earlier sessions here at the conference, RISC-V is based around the foundation, which is a consortium of users and members that come together to help form the alliances that help RISC-V develop. So just a little bit on the ecosystem. We cover the spectrum across the industry, from foundries, IP providers, OS support, simulators, EDA tools. All of this comes together within this community. As a community group, we have several working sessions. So currently, this needs to be a membership where you join the RISC-V Foundation and fully participate within these working groups. The good news is this is going to be changing in the new year, and these groups will be open to observations from people that are non-members. So if you're not a member yet, you can join, participate, actively contribute, and in the new year, you'll still be able to observe some of the working groups and activities. And then for you that are watching at home on the video that will be recorded and shown as the proceedings, the full slide set is also available to view. So within the bit manipulation working group, we've been actively participating, providing a reference simulator to help the early development of these instructions. And this works well for customers or partners that are looking at RISC-V and looking to add their own custom instructions. So a lot of these working group activities is very relevant to how a customer or a user can expand and use RISC-V. One of the latest developments within RISC-V, and you'll hear a little bit about today, is the new vectors extensions. This adds a great deal of capabilities to RISC-V and will be a new standard that will be released next year. And we've got some early progress work to show you on how we're contributing and helping with the verification. So for all of you that are sitting back, this is what I was saying about looking at the screen. We've got some key links here that show some of the resources that are available on GitHub. We have the compliance and reference suite. We have the latest specs for bit manipulation and vectors. And we have a free simulator, RISC-V OBP Sim, you can download and start using. So within RISC-V, as you may be aware, there is a number of options to how you can get to a RISC-V core. You can start with one of the commercial IP providers, and there's many of them available. We list here a few of the top guys. There's also open source cores. As I mentioned earlier, Open Hardware Group has a couple of cores. CHIPS Alliance has a core. Low Risk has cores. So there's many open source consortium work bringing together innovations and launching new cores on the open source environment. But RISC-V has this flexible framework. It's an open ISA that allows extensions. So the ecosystem of tools providers and infrastructure are helping users and adopters how you accommodate all these flexibilities. And these are some of the members that are within the RISC-V Foundation. And verification tools. So just a small plug, we're with Imperas. We do simulation and also verification with the project here today with Google. So as a marketing guy, you say, what is the requirements for verification and why is compliance important? So compliance is, in essence, the compatibility across the devices that implement RISC-V. This is good for the community, good for the users, good for the ecosystem. So how do we get all of this compatibility together? And there's no simple one-shot path. There's many techniques, there's many approaches. We're going to be talking today about some of the elements of verification we think are important, and hopefully you'll get some good taste of the further work. And of course, what we want to achieve across the RISC-V community is this compatibility that drives investment and reuse and software that's going to really help the whole community. So within the compliance working group, there's really two activities that go on. The main one is the framework. It's going to look to pull together all of these different suites for all the different attributes behind RISC-V. And then the suite itself is a dedicated functional test per module. Because within RISC-V, it's an open, flexible architecture, so different implementations will use different modules. So you need to be able to use the modules that are appropriate for your design and test the compliance individually. And I think I can now hand over to Lee Moore from our technical team, who will cover the more detailed aspects.
Thanks, Kevin.
Lee.
So good morning. My name is Lee Moore. So I've spent a lot of time on RISC-V. I actually got involved about 3 years ago. We had an initial implementation of a RISC-V model within our simulation framework. And I got involved with compliance 18 months ago. And that's actually taken up quite a bit of time for us as a company. Myself and Simon have been involved in work in the compliance working group. But in addition to the work in the working group itself, you know, we've been developing both the framework and the tests that sit within that framework. So I'm going to try and give you an update as to where we are with respect to the compliance. So what we have is a framework that's built, which Kevin has already told us a little bit about, and it consists of tests. We also need an assembler inside of there. We need a reference simulator, and the reference simulator is used, previously it's been used really simply as one of the targets of that compliance framework to ensure that the tests are written and produce specific results. Moving forward, we've sort of come to the realization that because of the number of permutations of options you have within the RISC-V ISA, that you can't actually use a static representation of a known good result of a test, because using different options from the ISA means that you know, valid tests will behave slightly differently in a given set of configurations. A very simple one to refer to there was something that has an ability to support misaligned load stores in hardware rather than taking a trap. Well, you can write a test that exercises that, and functionally it will be correct in terms of the results you get, but it will take a different path in order to get there. The reference simulator that we provide is we call RISC-V OVP Sim. You'll actually find this in several of the GitHub repositories. We have a dedicated repository for RISC-V OVP Sim, but also it's used as a component within the RISC-V DV and also within RISC-V compliance, so that when you download from the GitHub repository and you run this, it just automatically works without having to go and look at you know, external modules. So these are some of the things I'm going to talk about here. I'm going to talk a little bit about the compliance tests themselves, DV tests, design and verification, and how they differ from compliance. We'll talk a little bit about formal tools, simulators, emulators, and FPGAs. So what is compliance? And more importantly, what is not compliance? Where does compliance end and DV begin? So we have a lot of discussions within the task group itself. The task group meets once every 2 weeks. And quite often the discussions sort of stray into what you should be testing in terms of proving the compliance, but not encroaching on what happens within design verification. And I'll probably bring out some of these. So we tried to get a definition of this, and what is that definition? And we have lots of discussions about what should be done within the group itself. And as I say, you know, quite frequently it gets into the point where does DV begin and compliance end? So what we do say is that for DV, for compliance, we have to prove that the device works within the envelope of the agreed specification, and that compliance is the adhering of that specification. Now, actually, there was a nice quote given by Krista. I thought I had it in here, but maybe I've missed it. But what we're trying to do is prove that the ISA should be independent of anything to do with the microarchitectural implementation. So I think there was something like 60 cores that are available at the moment that are RISC-V implementations, and they'll all be different in terms of how they do this. They'll have different number of stages within their pipeline. They may have multiple issue. They may have prefetch, branch predictors. As far as compliance is concerned, we're really not concerned about that. We should only be concerned with proving that it's working within the specification. We don't care about things like out-of-order execution. We don't care about parallel execution, multiple dispatch. That's part of the microarchitectural implementation. Some instructions will be multi-cycle, some instructions will be single cycle. Again, from the ISA perspective, this is irrelevant. It could have a shallow or deep pipeline, and it could have a branch predictor within it. So there's a number of things here that you can attach to the microarchitectural aspects of the design, which are not intended to be investigated by the compliance group. One thing I will say, which tends to be a little bit contentious, which is, as part of compliance, the decision is made that we only attempt to test positive, in a positive manner. So if the intention is to exercise a device which only claims to support the base I extension, then it is not the job of the compliance to prove that it does not support the M extension. And this is quite interesting because what we know is there are some implementations out there today which implement subsets of extensions. And in the case of the M extension, we know there is silicon which supports the multiply but doesn't support the divide. And that's a sort of a strange situation. Do you test for the fact that it is absent, or do you test for the fact that it is present? And in the case where it's only half present, what does that actually mean? I did note from a presentation that was given earlier this week, actually, that it appears as though the M extension has been broken down into some subsets, and it looks like now there is a Z extension which defines the presence of multiply or divide without both of them being present as the encompassing M extension. Okay. So what is compliance trying to do? It's trying to test all the possible alternatives without trying to test the values. Because if you end up trying to test the data values and exercise the data paths, then the size of those tests are going to be pretty big. And again, it's really the job of DV to do that. What you want to do is prove that you have read and understood the meanings within the specification. In fact, this is the quote that, the statement that Krista made in the compliance members group earlier this week. And I think that's quite a neat way of phrasing what it is we're trying to do. Okay. There is a lot of overlap between compliance and DV. And as I said, we discussed this quite a lot within the group in terms of saying, well, you're going too far there in terms of your testing. You shouldn't be doing that. That's part of design verification, or you're not going far enough. And if you take the opinions of all the people within the group, you're going to get quite a wide variation. And actually trying to formalize this and say, well, this is actually the cutoff point between compliance and design verification is very difficult. But you can kind of visualize it like this, that the overlap is probably somewhere between that or somewhere between that. It's difficult to draw an accurate line. Now, when we run the framework, and I'll show this running in a moment, I've got some pre-recorded videos. But effectively, it looks like this, whereby you have a suite of tests which are specifically targeted against an extension within the ISA. So let's say the RV32I or the RV32M. You run that through a stage of compilation. You execute those programs on your design under test. For example, if you have an IBEX core. And then you also execute it on your reference. So let's say RISC-V over PSIM, which is the envelope model that we use in order to configure with all the given options you have within the ISA specification. And then you perform some comparison and you generate a report to say either where they compare successfully or where they differ. And then this sort of iterates around this loop until you got to the point where the reference model produces the behavior that's matched within the design under test. Now, what do these code snippets look like? I've extracted some of these from the actual tests themselves, just to try and explain how it looks. And typically, the flow is something like, loading some registers with values which will form the operands for the instruction under test. So here's one part of an add instruction. We load 2 registers with 2 values, 2 and 3. We perform the add operation, which produces a result. And then we write this the result of the add instruction to a signature. Now, the signature is an area of memory which is predefined that you populate with the results of all of the tests that you execute within the program that you're running as part of your compliance suite. And then at the end of the test, the intention is you have some method of extracting that data out and storing it locally so that it can be compared. And if you recall what I said at the beginning, there are 2 modes of operation. Currently, we have this static approach, and we're also looking at this dynamic approach. So what I'm describing here is the static approach, which allows us to extract the data and then do some comparison with whatever our reference is. But of course, that's a pretty simple example, right? That's not, would you call that compliance? Well, no, I don't think so. You've performed one operation using a specific set of registers for both the input and the output operands. So what we typically try to do is we try to extend this, and this is really just pseudocode here to indicate the kind of things maybe you should do as part of compliance. So should you have a walking 1 or a walking 0 that appears throughout the registers which are your operands to your instruction? So you could see how you could write something like that. It would iterate across the value in the register and then apply it to the instruction under test, and then it would store it into your signature file that you could compare later on. Right, okay. So in this particular example here, where we show a walking 1 or a walking 0, it's a pretty simple example. And also when applied to an add instruction, you're going to be able to produce the same kind of result on the output register as well. But there are some much more complex tests than this. For example, we're currently working on the vector extensions, and I'll come on to that a little bit later and explain the difficulty with testing vectors. But is this sufficient? In terms of what we have now, is just walking a 1 or walking a 0 across your operands enough? Well, no, it's not, because this is not going to test things like overflow, underflow, and so you need to try and extend this. And we've sort of discussed how we generate the sets of values that can exploit the behaviors, and so we typically choose things like corner cases, the most negative largest, the most negative number, the most positive number, the smallest negative, the smallest positive, zeros, things like that, and then also some other intermediate values that we can use as part of the stimulus for these tests. And then if you enroll them in terms of the data that you provide, then that's what you can use as part of your test. The problem is that you can now start to see you're encroaching on what is traditional design verification territory at this point. And in fact, if you were to take that to the logical conclusion, then what you would actually say is, hey, why not just iterate every possible value for every possible operand? Well, you're really now starting to get into deep water as far as verification is concerned. But one of the things we do ensure is that we do want to make sure that we exercise all the possible registers that can be used for the given instructions for the compliance testing. So we'll always make sure that for let's say an instruction that takes a 2-operand input and produces a result, then we want to make sure we iterate through x0 through to x31. We don't necessarily want to check the combinations, but we certainly want to check that we've exercised all of those. And so again, if you take that to the logical conclusion, what you're going to have is something horrendously complex like this that iterates across all the possible register operands and takes all the possible values. Well, if you do that, then you look at the number of instructions you generate, and it's a pretty big number because you're taking in combinations of your source operand registers, your destination operand registers, and also the values associated with it. And so this just isn't feasible to do this. So, what are the constraints that we have? Well, I would say they're not definitive. We discuss, and there are grey areas in terms of what happens as part of compliance, but they're not definitive. I couldn't have a specification written down on paper that I could give to someone and say, there you go, write to that. It's a lot of it is gut feeling to ensure that you've covered a lot of the cases. But we do define coverage for all of this testing that we do, and I'll show some of that later on as well. How much code and data do you have available in terms of the program that you're producing? We've never really come up with a constraint that says you must ensure that the amount of code and data memory that you take in is less than some number. In fact, if I look at the test that we currently have, at the moment it's pretty small. It's not something that really causes a problem. How do we handle large displacements, especially in the context of a test which has a small amount of addressable memory? There are techniques you can use, especially with relative addressing, so you can do things like using negative offsets to bring them back into range. But in some cases, you can't ensure that you can test a displacement for a branch or a jump to go to, in order to test what the parameters of the instruction are, because you may not have memory that's available at that point. And it's the same for loads and stores. So all of this just comes down to trade-off, trade-off, trade-off. It seems that whenever we're performing these tests, we have to always do trade-offs in terms of the amount of data that we want to generate, the size of the code that we want to generate, how long the tests take to run. It's a lot of horse trading in terms of what we need to do. So this is what we actually try to do. We try to use every possible register as both an input and an output, in the case where an output is produced, because sometimes we don't have an output. If we have a branch or a jump that doesn't use a link register, then there is no effective output register change. And in the case of immediate values, where we have things like offsets, displacements, shifts, or rotate immediate values, what we've tried to do is to take the smallest and the largest values of those offsets or immediate values, and then to produce values that have things like walking ones, walking zeros. So this is really affecting the correctness of the decode and additionally the operation of those instructions that use them. The kind of things we want to try and avoid is doing a simple two-state toggle where you have immediate values. You know, if you have a 12-bit immediate, don't just write a test that tests with all zeros or all ones. You know, we do want to take some distribution across those immediate values. Now, what I've talked about so far really is just the integer instructions, and there has been some work on other extensions within the compliance group. We have some tests for the multiply and the compressed instructions, and there has been work on floating point and single and double precision. But actually, when you get onto some of the other extensions within RISC-V, these can become very complex. As I mentioned, we are working on the vector instruction set. But if you compare these to the simple base instructions for integer arithmetic, then as soon as you get into things like floating point, it's really difficult. You know, you've got what are the choices for these registers that you want, the register values you want to exercise? You know, you can choose a minus max, a minus 1. In fact, the thing that's missing off there for floating point is, you know, minus 0 and plus 0, which you have in floating point, right? Infinities, it's very complex, and you can't just simply take, you know, walking ones and walking zeros. And again, as I said before, do not attempt to exercise all types of combinations. In coverage, you have the notion of both coverage counts for discrete values, but also cross-coverage. And we do some cross-coverage as part of the analysis in the compliance group, but we don't do cross-coverage in terms of saying, let's ensure that we've seen every possible combination of register operands in terms of their indexing, because again, it would just blow the amount of data that we have available to us. We don't try and exercise all possible immediate values because some of the immediate fields in the instructions are just too big, so you can't do that. And the same for branches and jumps. You know, sometimes you can't get to exercise all of the possible offsets. Same for load store. So, in terms of the compliance memory footprint, what does this actually look like? So we produce a text section. The text section contains the exception handling code, it has some startup code, and it has the code for the test itself, and then there's some shutdown code as well. Now, clearly there's no way of doing a true shutdown. Typically what it is, there's some magic instruction that you generate that your framework has to inform whatever the target is. This is the point at where the test ends. And in the case of a simulation target, that's quite simple to do. You just need to decode whatever that magic instruction is, and then you say, okay, that's the point where the test ends. The reason why I've put contentious in there about exception handling code, so one of the edicts regarding compliance testing is that, or, as I said before, it should all be positive testing. And so in the case of, you know, we don't attempt to test instructions which are not supported, i.e. multiply instructions for an integer extension. In the same way, you're not supposed to test exception handling code. So you shouldn't be writing your tests which you know are going to perform a misaligned jump or a misaligned load store in order to trigger an exception handler. That's the current position. I'm not sure that can be maintained because I think you do really need to test these things, but it's still under discussion within the group. And then finally, in the data section, we have data within there that has debugging and logging messages and also the signature data that I mentioned earlier. So how do we get this program loaded into our targets? Now bear in mind the targets really that we have inside of our system at the moment, inside the compliances, they're all simulation based. There have been users, for example, I know Microchip did some work where they took the compliance suite and they ran it on FPGA implementations of their real hardware. But in general, most of the work, I think, has been done against RTL simulation, against instruction set simulation. But if you need to load this into memory, these are the kind of approaches you take. If it's an ISS, you'll have a readelf capability. If it's an RTL simulator, possibly a write mem. And if you've got hardware, you'd probably load this through the debug mechanism via JTAG or OpenOCD, something like that. Then what happens is you allow the target to execute and run your test, and it gets to the finish point where it's completed the execution of the test, and then what it's going to do, it's going to extract the results out. And as I said, it will compare that to some golden reference. So what's required if you need to port this infrastructure to a given target? So you have to implement the macro body definitions, and you have to describe a linker script, because the memory layout in every target is likely to be different. And so therefore you have to be able to take the test case that we produce and to be able to locate the data and the text in the correct areas for whatever the target is that you're going to execute on. And if we look at a full piece of code here, you see we have the RV32I add instruction there, and then we have the linker script. And in fact, this was the linker script that was used in order to format the data for the IBEX core. And we, as part of the compliance testing, we took the IBEX core and we ran the compliance suite against IBEX RTL running inside of Verilator. So I showed this slide before. I'm going to quickly show a video here of it running. So this is the kind of flow you have where we have a suite of tests within a given extension, RV32I in this case, and we execute it on the target and also provide the reference. So hopefully this is going to run straight away. So I'm going to show here this running on my machine. So in fact, this was using the metrics cloud-based computing. So there's going to be a demonstration given later showing the capabilities of within metrics. But we set up a project so that we could execute compliance, coverage, design verification, all within the metrics cloud using their RTL simulation capability, but also using RISS as part of the methods of doing the verification and compliance. So what you're seeing here is me just running the compliance framework. So it's all make-based. I've got to set up the correct parameters, and it runs pretty quick. Bang, that was it. So what that actually showed there is running all of the RV32I tests on the ISS. Now, how do we measure quality? I mentioned about coverage. And so we have coverage metrics built in that we can analyze, and we generate coverage based upon the data and also some cross coverage as well. I was going to go into this, but I think I'll leave this coverage because the time's going quite quickly. But what is important is how we look at this coverage. We look at the data that's been executed from the test, and we can generate information that tells us where we should focus our efforts in terms of getting good coverage for the entire suite. And in fact, I'm going to miss some of this as well. Say again? Do I? It's on 60 there. Okay. All right, okay. So let me go back a little bit then, if I do have more time. So this is what our coverage looks like. You know, we're monitoring the fact that we're targeting specific registers. We're using specific registers as our inputs. And we're also looking at some of the data in terms of things like the data values themselves. Are we accessing things like positive, negative numbers, and using that as part of the coverage analysis that we generate? So if I was to look at a simple bit of code snippet here, we see that we have a sequential set of add immediate instructions where we're iterating through the immediate value in order to get some additional coverage as part of the immediate value decode. And as I mentioned before, the typical flow is you perform an operation and then you store the result of that operation into memory as part of the signature. And what you do is you compare that signature later on to some reference. And if you look at something here, we've executed 6 instructions and stored the result, which is great, right? That's going to improve our coverage. Well, the fact is actually it doesn't. And this is one of the things we have to be very careful of when looking at the results of coverage, because what coverage tells us is what's been executed. It doesn't say it's been measured, because remember, in compliance, the measurement is done by the contents of the signature file. So in this case here, there is only ever a single store word at the end of this sequence of instructions that writes a value into the signature, meaning that all the previous instructions executed, the values they produced are actually discarded. And this was a little bit of concern that we risked the fact that with the tests we were creating, although we could generate the coverage, we couldn't be confident that the coverage really represented the propagation of the test itself into the signature that was giving us the pass or fail status. So we had to start thinking about how we could fix this, and this is really showing what the problem is, right? So if I showed this in a hardware representation, if you have a sequence of ones and zeros going into some function, here we show an AND gate, and we have a coverage point measuring those values as they come out. Those measurement values that we have are only valid if they appear or they cause an effect on the signature that we're producing. And if we cut that wire such that the data never propagates, then effectively you might as well put them all in the trash can. And that's the risk. And so what we did in order to ensure that the test quality could be definitively known to be propagated into the signature file is that we used a mode of our ISS in such a way as we do a thing called mutation testing. And what mutation testing does is that it puts a fault injection into the execution of your program. And I think there's actually a reference there to something online. If you see the slides afterwards, you can follow that link. The way mutation testing works is you're effectively saying, if I have an if-then-else branch, the condition that's tested, you flip the sense of it, and you say, okay, is that measured at some point later on? And if we went back and looked at the previous example where we had this stream of instructions, and what we said is, okay, what we're going to do is mutate that first instruction to prove definitively whether or not it does have an effect on the signature you produce. Well, this would actually prove it. What we do is we say, okay, let's replace that first add immediate instruction with a NOP operation, so an add that targets X0 and uses X0 as its input parameters. Now, if the result that we get is the same, irrespective of which way you flip that instruction, then you know that the instruction, even though it's contributing towards the coverage, you know that actually that is not valid. And this is very important in order to be able to fully validate what you have in terms of your test, because you're doing the coverage that says, hey, this is the intent of my test and this is what I'm seeing, but then you also have another check further on that says, well, actually, that didn't have any effect in terms of the propagation of the data. Oh, question? So the question is, with mutation, you're expecting the test to fail, and that's absolutely correct. So what you're looking for is the fact that in terms of your contribution of coverage of a particular instruction, the premise is that that instruction is changing the result that you have. And if you introduce a mutation, and it's the same result, then you're effectively saying, well, that instruction had no effect. Whether it was present or whether it is omitted from the instruction streams, you got the same result.
Thanks for taking the question. This is Rajesh. So here the intent of mutation is to kind of measure the quality of your compliance test itself.
Correct,
rather than the DUT itself.
Exactly. That's right. It's trying to measure the quality of the test, because it's very difficult when you write these tests that, and in fact, okay, the integer tests are trivial in comparison to some of the other work we're doing. And so you could probably sit there and hand calculate what the results are. Say, hey, I'm doing this operation, I expect this value. I'm doing this operation, I'm expecting that value. When you get onto some of the really complex tests, such as the vector operations, and when you get a high volume of tests that you're performing, you sort of get to the point where you say, for a majority of this, I'm going to have to trust the reference that I'm executing this on in terms of the results that are produced and what I'm going to use to compare to my device under test. And if you're going to do that trust, you need to have a way of saying, okay, so I need to ensure that these things that I think I've tested have actually propagated to the result inside of the signature file. And in fact, I don't mention it in this presentation, but I mentioned it yesterday. Somebody put an issue on the compliance GitHub regarding the compressed instruction set tests, where they said, hey, there's a bug in this test. You're actually calculating a value, but you're writing it to an address that's outside the signature area. So, and I thought, oh, hang on, that doesn't make sense. How can that be? Because we did all this mutation testing. Well, actually, we only did the mutation testing on the I set. And for the compressed set, we didn't actually run the mutation testing. There's still a to-do there to go back and run this on some of the other tests. So yeah, even though something is reported as being covered, which is great, it says, hey, you've tested that instruction with these operands. If it doesn't propagate anywhere and it's never measured, it might as well have never happened.
All right, thank you.
Okay. So there's sort of two types of mutation testing that we put in here. One is, just replacing an instruction with a no-op and seeing if that causes the signature to differ. But also what we do is we toggle individual bits of part of the decode, for example, in your immediate values, and we look again to see, does that propagate an effect? And so in the case of an add immediate here, you can see that there are 12 bits of an immediate field, and then there are bits for the decode, and there are bits for the register indices. And so if we look to that in terms of the decode pattern, anything that you see there as a dot is indicating these are places where we can toggle those bits and see, is there an effect of the result that we produce. Okay. I'm going to skip some of this. So that's right. So these are the approaches we take with mutation. We do NOP replacement and we do bit inversion. We have to be careful not to invert the bits of the decode, because of course that changes the intent of the instruction itself rather than what the instruction is attempting to do, and that can cause things to go completely wrong. Okay, so this shows an example here of where you would generate 23 fault models for a given instruction. Does it actually show all of them? I think it does. Yeah, it does. Here we go. So in the case of an add immediate, this is the kind of thing you do. The red there is indicating bits that you're not going to consider changing. But here we can see where we bit mutate parts of the immediate value, and then we have that run through the simulator and see if we get a signature result. Signature difference, sorry. Now this actually has to be very efficient as well, and what we don't want to do is to have to change the binaries. So this has to be a capability within the simulator itself. You know, we don't want to recompile code all the time. That's very inefficient. And so what we do is we run all of these fault models within our simulation environment using a very smart technique, and I can show you a quick demo of this as well. Ultimately, what we're looking for is to see whether the contents of the signature are modified by introducing the mutation. And what we do want to see a failure in that respect, because a failure indicates a contribution to the signature difference. So, by running the mutating fault simulator, we effectively grade the coverage of the compliance suite. So now, you know, this is an interesting approach, because when we first started off, the goal was really to write tests. And then we looked at the tests and we said, how good are these tests? You know, we don't really know how good these tests are. And then we said, okay, we're going to put some coverage in. And we added coverage in order to look at the tests when they ran to say, how good are those tests? And then we said, how good is the coverage? Oh, okay, we need to grade how good the coverage is, and we have to then do this test that says whether or not the coverage that's been produced for the test is actually valid or not. So I think we're in a position with this flow that it's quite robust. But what we want to do is we want to automate this in terms of getting these coverage metrics. So let's show this running. And, you know, so this demo here, you know, there's not an awful lot to see, because this is really just you execute your environment in a certain manner, and then you get a report out at the end that says whether or not things were detected as the mutation causing a difference. So the only way really to show this is the throughput, because when you introduce faults into your executing tests, you want to make sure that the throughput is fast. And what you're looking at there, if we look at the window on the left, you see the number of fault tests that have been introduced, running it against a given ELF file. So we're sort of up to 14,000, 15,000 tests. And on the right there, you'll see the way our simulator works, in that it has high levels of parallelism and multi-threading. And that's what you're seeing it running. So it's not as though multiple instances of the simulator are running. The way the simulation engine works is that it can continue executing the code linearly until a point a mutation occurs. And at the point the mutation occurs, you effectively get 2 copies. And at that point there, you can continue executing. And you may have a reconvergence at some point, which means you collapse back down again. So it's important for this to be very efficient. OK, so what I've gone through there so far is a lot of detail about compliance testing. And I want to just go on to where we are with some of the recent work we've been doing. So we began working on the vector extension testing probably about 2 months ago, I'm guessing. And the vector the vector unit is incredibly complex when compared to any of the other extensions that we've looked at previously. Here are some of the tests that we've actually coded up so far. And we're at the point where we have about 2,000 tests. Now, compare that to where we were with RV32i. In the compliance suite, if you look at the RV32i test, there are 48 tests that test all of the instructions, all of your adds, subtracts, your shifts, your rotates. Sorry, there's no rotate, that's in bit minute. Shifts, load stores, all that kind of thing. 48 in total. We're only partway through coding up for the vector instructions at the moment. We're about 2,000 tests as of today. And we estimate that there's going to be more than 10,000 tests that are required. And this is compliance. This isn't DV at this point. We're just talking about compliance. And remember when I spoke earlier about the difference between compliance and DV and how much more detailed the DV tests have to be over the compliance. So now this kind of shows the potential problem that we have to solve here. By the end of this, we expect to have 10,000 plus tests. On the tests we currently have, with the coverage metrics that we're using, that we've discussed within the compliance working group, and what have currently been agreed, we're getting 100% coverage on those instructions, which is great. However, it's begun to slow things down. You saw how quickly that executed on our simulation environment there. And that was actually executing everything linearly. I'm not talking about the mutation testing, I'm talking about the compliance testing. And one of the things we've had to introduce recently is to parallelize a lot of the compilation and also the execution. However, you know, on my own machine, which is an 8-core desktop Linux machine, I can run those 2,000 tests in about 30 seconds, which is pretty impressive. Now, that's not the same as what it would be on an RTL simulator or a piece of hardware, but of course, in our environment, which we're using for the majority of the testing, you know, we can get through that very quickly. So that's the end of the section on compliance. I'm just going to touch on some of the work we're doing in hardware design verification. So this is sort of like the next level along. And some of the things I'm going to talk about here are not in slides because it's very recent, and I haven't been able to add them into the slides here. But as far as design verification is concerned, there are a number of ways of handling this, and there are a number of tools and methodologies. So what do we have? We have, at the moment, we have a reference model, we have compliance tests. You also require directed tests. So directed tests are different in that you're trying to begin to exploit both parts of the architecture, but also the microarchitecture. And remember that the microarchitecture part is going to be specific to every implementation of a RISC-V specification. And you also need things like random instruction generators, and Simon will talk about this later on, the work we've been doing with both Google and Metrics in order to encapsulate this into a nice flow where you can produce stream-generated instructions to exercise parts of the specification. But you also need things like formal models, and we use things like SAIL as part of the compliance flow, but also instruction set simulators, RTL simulators, FPGAs and emulators all need to form part of this. And the goal here really is to test and test and test. And I'm sure everyone in this room is aware, you know, your testing is probably never done. All you can really do is try and prove beyond what is a reasonable doubt that you're meeting whatever the objectives are, and you've teased out the issues that may be present in your implementation. And from this, you have your architectural tests, of which the compliance group is forming, you know, a majority of that. But there'll be things that are not covered by that. I said, you know, that we don't attempt to execute all the possible data alternatives. And then from the microarchitectural, this is where you get down into the real detail, nitty-gritty of the implementation itself. And you've got to prove that your pipeline operates correctly, that hazards are resolved. If you have speculative execution, that speculative execution doesn't end up being committed to either your register file or to your memory. And also if you have branch predictors that they're working in the way that they intend to, and also multiple issues. And compliance can help with this, stress tests can help with this, but you also need things like the instruction stream generation as well, pseudo-random. And that helps you in order to do your detailed testing and try and show some of the bugs that are present or potentially present. What are the tools that can help you with this? Well, instruction set simulators, cycle-accurate simulators, virtual platforms. There's a whole range of possible targets that you can use for this. And even going all the way to running your tests on the physical device. It's far better to catch these things early on, as we all know, and you always need a reference in order to do these comparisons to, and that's sort of the thing that we're doing. So what's not covered on these slides, which I was just going to talk about here, is that some recent work we've been doing is that we also need to provide our reference as an embedded component within an RTL simulation, because one of the things that's clear is that doing the post-process operation of running tests on a design against a reference is not useful, because it's after the fact. What you really want to do is you want to catch the divergence between your reference and your design under test at the point where that divergence occurs. And so what we've done is we've taken the RISC-V OVP sim executable environment that is part of this whole process and is available on GitHub, and we've made it so it can be embedded within a System Verilog simulation. So System Verilog provides what's called the DPI, the Direct Procedural Interface. This allows you to take a foreign module and embed it and provide a way of giving transactions onto the rest of the system. And we've implemented this inside a System Verilog with our reference model, so that it means you can exercise this in parallel to your design under test. Now, the real benefit to this is that it's simple in Verilog to write a compare routine. So long as you can get access to the right parts of the design, you can see where the program counter is stepping through your design, your program, and you can see the data that's being written back into your register file or into main memory through loads and stores. This means that being able to access those, you can compare them on a cycle-by-cycle basis. So that when there's a divergence, you can just halt the entire environment. And because you have great debug capabilities, both from Verilog simulators, but also from our perspective, we have a multiprocessor debugger that can look at the contents of a design. It means you can take the entire state and work out why there's a divergence. Doing this same work by simply comparing log files is incredibly difficult, especially when you look at what we have in the compliance group, which is a signature. I mean, that's absolutely useless, to be honest, for debugging. Just comparing a whole memory dump against another memory dump doesn't help you go back and find the root cause of any problem. Embedding this within this environment, it means you stop at the point where it diverges, and you can compare the state from the RTL implementation and the reference implementation. You can look to see, okay, if an exception happened, why did the exception happen? What was the data values that caused that? If it's an exception for a floating point reason, something like that, you can look at the entire state, both from the general purpose register perspective, but also from the machine state CSRs. So it's a unfortunately, I don't have a slide of that in here, but that's basically what we've been working on recently. And that's the end of my bit. So I'm going to hand over to Simon. He's going to talk about the instruction stream generation that we've been doing with Metrics and Google.
Yeah, I mean, just before I start, were there any questions for Lee? We could probably do a Q&A session at the end, but just if there was anything following on from that bit. Okay, we'll think about them again at the end. Okay, so thanks, Lee, for that. So what Lee's been talking about there really is the compliance side of it and verification. And actually, there isn't a lot of difference between compliance and verification, apart from the amount of testing that you do and actually some of the ways you probe inside of the design. But compliance is the beginning of verification. And almost everything that Lee talked about there, it is verification. It's just something that as an industry, as the foundation initially started, the RISC-V Foundation, we're trying to make open and available to everybody. And what we're talking about here this morning really is what we're trying to have to take that further forward so we can do more verification, not just compliance, and move that forward. And we're doing that more in the auspices of the CHIPS Alliance and the Open Hardware Group, which Kevin mentioned at the beginning, in that where they're trying to take cores and make those reliable and robust and easily usable by the industry, by the community. And so we're working to try to take a verification environment for them and build that forward. So what I'm going to do is to talk about a part of this flow. Kevin showed this slide, and I just showed it there. The left-hand side says Google Cloud at the top of it, a UVM stream generator, and that's what I'm going to be talking about here. And Lee talked about the flow, and what the purpose of this component is it generates assembler files, basically tests to drive through. Up to now, Lee's been talking about compliance tests, really. And that's where we very carefully sort of hand code those and create those. Actually, we do use a generator, but it's a very specific generator to do that, which looks into certain corners and things. This stream generator, and I'm going to talk about it, how we can generate just as many instruction streams as we want randomly, but in a constrained way. And this has been developed by Google, by the Google Cloud team, based on work that they've done internally and the chips, the designs they've been verifying. And what I'm going to talk about, what their motivation was and what the existing solutions were. And I think it was yesterday, Wednesday or Tuesday, their lead engineer actually did a presentation on the state of that and where they're taking that and roadmap. And what I'm talking about is what is available today here, and talk about that. So one of the fundamental things in our industry is that we want to have reuse. Why do we buy a processor core? Well, because someone's already done verification of it and it does a job and we can get a specification. And design verification is an absolute fundamental technology in enabling this reuse. And if you want reuse, quality is an unbelievable component of that as well. And to get there, you have to test things and test things and test things. And as we all know, DV is one of the biggest components in the budget in design of modern electronic systems. So it's a key component. And if we look at, a year ago, as Google were looking to develop a testing methodology for what they were doing internally, they looked around and there were two open source repositories that had actually come from the work from Berkeley in the early days in Sci5, I think, where there was some simple testing. And they looked at those to see if those could help them. And actually, I think everybody probably downloads those and does use those. And, they're pretty good in certain ways, but they're very limited in certain ways as well. And there's many missing components in there in terms of they don't have a detailed branch structure. They didn't do a lot of exception things in there. They didn't do the compressed instructions and things like that. And so there were lots of bits that they were putting into their silicon, but actually that they couldn't find tests for them out there. So they wanted to build a much better solution in there, focusing on their hardware verification to build an infrastructure. And in the philosophy of Google, they were doing it in a community way, wanting to make it open source, make it available. So it wasn't just for an internal engineering effort that they were trying to build it. And the result of that is this UVM stream generator. They made a decision to use the UVM components of System Verilog, which requires System Verilog simulators to use that. But they were going to write this test bench, this generator, in an open source way and make it available, and also try and solicit contributions from other people in there. And the goal was not to do the sort of simple testing, but to try and push their RISC-V designs into the corners and really flush out the issues that they were concerned would be in there. And there were several sort of key features of this, and I'm just going to touch into a couple of these. It's a constraint-based random generator, so it's going to generate random streams of instructions, and I'll talk more a little on the randomness. It needs to be architecture aware. It needs to not just be creating random instructions, because you don't want to be switching in and out of privilege modes and causing exceptions and doing silly things. It needs to be sort of smart in some ways. And actually, when they talked in the presentation this week, they started talking about trying to learn maybe some machine learning technologies around the top of it to help to not just constrained random, but actually smarter on there. But it needs to be architecture aware. It needs to be high performance, because you need to generate tens of thousands of tests and have complete automation is the idea. And then it needs to be extendable in the same way that the RISC-V is extendable. If you want different instruction sets, you should be able to add those to it. It shouldn't be just fixed and maintained and developed by them. The whole idea is it should be available and extendable. Talking about randomness, there's several different types of randomness that you need to be considering there. Simple randomness is, which instruction follows which instruction and what the data and the operands and things and data is going to be there. But also you might want to do things where you're interspersing things like bench instructions and between load stores and things like that to take into account the architecture that you've got there, and maybe talking about caching and things like that. So there's different types of randomization, sort of instruction level, sequential, etc. And The instruction randomization is actually very simple, and that's what the previous sort of open source solutions that they found a few years ago were very simple to generate some instructions, to put operands in there and some values. And it's quite simple to do that, but actually things like branches get very difficult, function calls and stack and all that sort of stuff gets pretty difficult too, and related to it, and different instructions like the CSRs, it's very easy to switch modes and things like that, which dramatically changes things. And as we move further into the vector instructions, there's a specific hardware that you can configure and say, this is my hardware device, like you've got a 32-bit RISC or a 64-bit, you can say, this is my vector engine and how wide things are. But then for each sequence of instructions, you can configure the engine to talk about how wide the elements are and which registers to use. And so every instruction is actually sort of polymorphic. And you can imagine the complexities of trying to set up legal sequences for vectors is quite a challenge. So there's a lot of consideration of that has been built into the infrastructure so that you can control it in a specific way, but then also get the benefits of randomization in there. So an instruction randomization is the sort of the easy part of it. It does need to be things like architecture aware, based on things like your branch predictors and things, because the whole idea of DV is you're trying to stress your hardware and push it around so it fails and does the incorrect thing. So it has to be pretty smart, and it has to be able to be controlled so that it is applicable to different architectures in there, whether those are with virtual memory or whatever. And then you get into issues where you've got multiple issue of instructions, even out of order things. It wants to take that into account as well. So it has the ability to put sequence of instructions so you can basically try and push hazards and things where you've got read after writes and things like that to try and affect the way that instructions flow through your pipelines and through the execution units. So it's actually pretty sophisticated. And I've been involved with verification for a long time. And I came across the Google stuff at a presentation they did at a RISC-V event, and I was astonished. I thought it was an interesting presentation. And I went outside afterwards to talk to the speaker from Google, and I was surprised to find him in a corner, and there were about 4 or 5 of the processor IP vendors in RISC-V, had him in a corner talking about it, sort of asking him how he did this and how he did that, and it was actually quite interesting. And the key thing they said is that there needs to be something very sophisticated, and we don't all want to build it ourselves. We want to try and work together and put something into the community which can do it. And the one thing that I heard them all say is how much better this Google generator was than other things that they had come across. So, and we actually then started playing with it, and actually I've been very impressed with what I've seen. I mean, yes, it's a lot of system Verilog code, it's open source, you can go and look at it. Actually, I'm not sure we've got a link up for it on one of the slides actually, but it's very easy to find it. And it's a lot of system Verilog code, sure, and some scripts and Python, but it does a very good job of the instruction streams it creates, and it's very efficient like that. But anyway, it tries to push the design about, and there's quite a lot of different components in it in terms of, and this is just the generator bit. This is nothing to do with the controlling of the targets or the reference or the compares or the coverage. This is just the generator bit. And there's a whole flow where it does it in certain controllable steps. It starts off with a program header, sets the privilege mode up. Again, you can randomize at each stage, but once you've set the privilege mode up, most of the time you don't want to change that unless you're actually trying to tackle that bit of the verification. Goes through things, page table stuff, initializes. There's a lot of subroutine stuff. You can do many depths of programs. You can say, I want small programs with a lot of function calls, or a few function calls with lots of large programs, and it's got a lot of dials on it. And there's actually a configuration file, and that's is actually all moving, so it's controlled by a YAML files outside it, so you can choose what the target ISS is, what the target design is, what the tests you're trying to test, which part of the design you're trying to test, and you can configure lots of the parameters of it, and go through the branching, stuff like that, working through you can even add your own directed instructions in there, so you can put sequences that you want to specifically to get it into a certain state, if you need to do that, and how it measures things and does interrupts and traps and all sorts of stuff. So it's actually pretty sophisticated, and I can't say it's the easiest thing to understand how the internals work, but as a user, you shouldn't really need to have to get into that. From an Imperas point of view, we've had to get into it actually in a lot of detail because we've, as Lee said, we've been adding the vector stuff into the compliance suite. We've also been adding the vector stuff into this environment and the bit manipulation stuff around this Google environment. So we've actually got all the sort of functional coverage in there for the vectors in there, all 500 odd instructions. That's how we're measuring them as we're developing them. So as a user, you shouldn't have to get into the too much of the internals. You'll have to take your design and put it into the flow somehow. And that's part of the work that we're trying to do with the Open Hardware Group and Chips Alliance, is to make it so that there is an environment that you can just download and run a core and have an example of it all working. And actually IBEX, the low-risk guys, have already got that available. So you can actually download, get their RTL, you get the stream generator, you get the reference from OVP Sim, and there's a flow so you can actually do generate and all the way through to comparison on it. So you can see how the RTL flow works. It's evolved quite a lot. It evolves quite quickly. There's a lot of work going and a lot of focus on it, and there's going to be more people in there. But there's quite a lot of features in there. It's quite a sophisticated environment and getting better, and I think it's a fantastic thing for the RISC-V community because verification is one of the big challenges, I think, and this, I believe, will help an awful lot with that. And with that, I think I'm going to pass to Doug to come and talk about how we've been talking here about the generator and things. Doug's now going to talk about the simulation and the verification bit of things. And one of the things I would say is that one of the things that Lee talked about is that, as we've been doing the testing, as we move to things like the vectors, okay, the compliance suite for RV32i is 50 tests or something. So it's very simple. When we come to things like the vectors, we expect some 10,000. And one of the problems with that is if you've got RTL and you're trying to build a vector thing, that's going to take a long time. And that's really where metrics comes in because they work in the cloud and it gives you pretty much infinite Verilog simulation there. So with that plug, so you don't have to do too much of a sales pitch yourself, let me pass to Doug here. So I'm just going to, I'll let you do that, Lee. So thanks very much.
As Simon was saying, we've had a cooperation with Imperas and Google around how to incorporate the Imperas reference models into an actual DV verification environment. And I think what I've noticed in the RISC-V community where metrics ourselves, we come from a more broad DV background, providing simulation type tools similar to the Synopsys Cadence Verilog system Verilog simulation. So I think the RISC-V community here are focused a lot more on the ISA and now starting to see more of the focused on productionized implementations, as we see with groups like CHIPS and the Open Hardware Alliance that Metrics has actually joined to be part of, along with Imperas and others here, is the focus coming in on verification, which is what really in the hardware design world is the hard problem these days. I mean, I know we, for example, to use the incumbent competitor to RISC-V, I know the teams at ARM spend, you guys have probably heard all these kind of numbers before, but our contacts there say that they spend 70% of their design efforts on verifying the actual chip versus versus designing it. And as RISC-V matures, that's where it has to go as well, right? As people are starting to put these things into actual tape-outs of semiconductor devices. So, metrics can play a key role in that, along with people like Imperas and Google. And I think you've seen here already Simon talking about the Google Generator piece of this, which, really the three components that are listed there from the previous diagram as well are the Google Randomized Generator, the Imperas Reference Simulator, because you have to have a good reference to test against, and the metrics, both simulator and platform that this runs on. So in a couple of moments, I'm actually going to pass to my colleague after a few slides here I've just set up to actually run a live demo of how that hardware verification process really looks in a real world setup, or at least in the metrics version of a real world setup. But I'll go through a little bit more detail on the pieces, and Simon's already done a good job of explaining here how the first piece, the Google Uvm Generator works. And the key thing that maybe I should add to what Simon has already said about this is that the generator itself is written in UVM, so System Verilog language, and that needs a proper compiler, System Verilog compiler. So that's part of the piece that we're contributing here and is typical in that world. And I think the key to this whole generator is the extensibility. Out of all of the things that Simon covered, the extensibility is there because really you're going to develop unique systems, right? I mean, you're not going to just take somebody's core, run the existing generator, and call it done, right? You need to be able to extend this thing, and most of that effort, as I was saying, is put into the effort of extending the generator to create test coverage that you need. And so I think that's the key piece to think about, and that all runs on top of a System Verilog simulation engine as well, as you'll see in our upcoming demo. So coming back to the main setup of the environment here, I think earlier actually Lee talked about how you can now incorporate their reference models into a live simulation, and I think we're cooperating with them to build that version of the demo. But the demo that you're looking at so far right now is a fairly simple setup, where, as you can see in this diagram, the Imperas reference model runs as a separate component alongside an RTL simulation provided by Metrics. Here, as you can see there, the one that has the open hardware RISC-V core mentioned in it. We actually have tested this with a few different cores. I think in fact our demo right now is going to use the IBEX core, but we've used the open hardware core that comes out of Pulp and some other examples as well. So I think as Simon had said, the Uvm generator here generates a RISC-V instruction program which needs to be compiled to an ELF and then go through the two parallel paths. However, in the future it'll be a more interactive environment where all this is live and streaming instructions in and comparing cycle by cycle in a more typical environment. So the key thing to notice about the diagram here is that you need RTL simulation for both the Uvm generator itself and the RTL core. And of course you need the reference simulator. So I think the whole previous hour of the presentation has been about the capabilities of Imperas' simulators. So I will just allow you to read the details of this slide on its own, but obviously you need to have that high quality reference to compare against in a DV flow like this, or else you're not going to get very far. And then for the piece that's the metric simulator itself, as I mentioned, we provide a simulation engine there comparable to what you get from a Synopsys or a Cadence, Synopsys VCS type System Verilog simulator tool. So it's fully compliant with IEEE 1800. I know in the world of RISC-V here, tools like Verilator are very popular, and as an open source fan, I think that's great, and in some cases those can be used. But when you get into professional level verification, as we're talking about here, and running complex UVM type tools like the generator that Google has put together, you have to have the full capability of the System Verilog language in the way that a production professional simulator provides. So that's the ability that you get out of using the flow that has been put together here by ourselves and Google and Imperas. The further piece to that is that you have to run many thousands of tests, and as you build SoCs out of these chips, they become complex designs that can run for even hours in certain cases, and you have thousands of those to run. So you need the kind of compute capacity that chip design companies typically run on thousands of machines. And we're lucky that in the era of cloud computing, we can all have access to that for at least for a much more reasonable cost and such than would have been true maybe 5 or 10 years ago. So the demo that you're going to see here in a moment is run on the Metrics cloud platform, which provides not only the simulator, but the infrastructure for scalably executing all of those simulation jobs in the way that a typical production DV flow would do. Yeah, so with that, I think probably a good time to jump right into our actual demo, and I'll invite my colleague Amy Sutton up here, because she's done most of this work along with Simon's team and Lee, so she'll do a lot better job of actually showing what that looks like than I will. Amy, please, I'll let you have it.
Hi, everyone. I'm Amy Sutton from Metrics. I'm here to tell you a little bit about Metrics and how we can help facilitate your RISC-V verification efforts, and specifically to show you our contribution to the demo that's been put together with Imperas and Google. So what I'm sharing with you right now is actually a diagram that explains the workflow of how users interact with Metrics. So Doug told you that we're a cloud-based platform, that we have a system Verilog simulator that we host in the cloud. And the diagram is meant to give you an idea of how, as a user, you can interact with Metrics. So the icon in the top left-hand corner represents your team of designer verification engineers, and the arrows on the bottom and the top represent your two interfaces to Metrics. Okay, the one on the bottom is through your Git repository, and the one on the right is through your web browser. So Git in the Metrics world is a first-class citizen. Git is our mechanism for getting your data into the cloud. So the way we do this is by cloning your Git repository, and then using that, we're able to launch an theoretically unlimited number of simulations in parallel. And we can do this because we have cloud resources for simulation as well. We have our own simulator, so we don't have restrictions when it comes to licenses. And you can see how in design verification, this is a big advantage because coverage closure tends to involve running a large number of simulations. There's never enough simulation resources or licenses when you need them. And we believe that going to the cloud is a way to address this problem. Okay. So as your simulations complete, we publish the results to a database that we also host in the cloud. So another thing that plagues people who are working in DV is storage of simulation artifacts. RTL simulations are infamous for generating large waveforms, large log files. People run out of disk space, and those are problems that we take away from the users. And then the results of these artifacts are published to a web application that we have developed to help you with your DV tasks, and that web application can be accessed from any web browser on any machine. So that's a bit of a summary of how you work with Metrics, and I will show you a bit about what our web application looks like. And I would like to also talk a little bit about our work with open hardware, and we're also a member of CHIPS Alliance. But yeah, we believe that our platform is ideal for open source and distributed development projects, partly because of our support for Git and GitHub and our use of the cloud, and also because we support a continuous integration workflow that's very useful for distributed teams. So with the open hardware group, they're going to be using the Metrics platform. We've donated our simulator for their use and our platform to help with the management of working with distributed resources. So I'll show you Just a few things about the metrics platform, and then I'll leave the last 5 minutes for questions because there hasn't been a lot of time for that, and I'm sure people have thought of some by now. So this, let me start here. This is the dashboard screen of our platform. So it's designed to give users a snapshot of how their project is progressing over time. We talked about, or previous presenters have spoken a lot about functional coverage. In System Verilog, there's also the concept of System Verilog assertions. So those are metrics that are very important to track because they give you a sense of how close your project is to completion. As well, we have another chart that shows you the ratio of passed versus failed tests. And in a realistic development effort, you would see trend lines here, and ideally you would see them approaching 100%, so that you would know that your project is close to achieving its goals. And I'll go back to show you the results screen. So this gives you quick summary information about your last several batch simulations, and it gives you all the critical information on one page. So in this case, this data all came from running the IBEX RISC-V core, and the simulation results are the results of the test bench that was shown in the previous slides that basically consists of using the Google generator and comparing the results of Imperas' ISS with RTL simulation. So in this suite of tests, there is actually only one test, but it's a random test, a random sequence of instructions. So every time you run it, it actually gives you different results. And the numbers that are displayed here show you the results of merging all this data into a single metric. So when simulations complete using the metrics platform, we automatically merge the results to give you combined numbers for functional coverage and assertion coverage. So that's a job that the user doesn't have to worry about at all. We display those figures to you automatically. And by clicking on these links, this will open a coverage report in your web browser where you can go through the coverage hierarchy and then look for any holes. So you can look for what's missing. And you can focus on things that are not covered. To help with this, we have filter capabilities. So if you only want to see things where the coverage is 0, you can add filters for that, and the green stuff disappears. You can see the red stuff here showing certain instructions were never covered in this particular test suite. We also have another feature, which we call test ranking, which people in the DV industry might be familiar with. Some others may not. But when you click on this tab that says Merged Sources, what this does is it ranks all the simulations that were run as part of this suite of tests, and it ranks them according to their contribution to coverage. So the first one typically has the highest contribution, and each one makes a smaller contribution on top of that. This is really important because it helps you to both eliminate redundant simulations and focus on the stimulus that gets you the biggest results. So in this case, if I kept scrolling down, eventually you'll see that some of these have 0 contribution, or very small and then 0. So technically, you could optimize your suite of tests to focus on the ones that are giving you the biggest coverage, and then perhaps write directed tests to fill in the holes. It's just one example of how this kind of analytics can help you to achieve your coverage goals faster. I'm not doing a really good job of leaving time for questions. I'll mention that Metrics has other debug tools that we also host in the cloud, that you can view log files and waveforms using our platform, which is also a great feature for distributed teams, because you can share data really easily amongst team members. And I'll just quickly show you a log file that came from running the IBEX core. So this was a failed case, and you can see this is comparing the RTL log with the one generated by Imperas' OVP sim and showing you the mismatches. And I think I'm going to wrap up there and leave it open for questions. And if anyone has questions for me, please go ahead to the microphones or any of the other speakers. There's some people. This is great. Hi.
Is this all open source?
Is our simulator open source? Was that the question?
Yes.
In the RISC-V sort of world, there's a lot of open source and there's a lot of commercial tools.
Yeah.
For example, I talk from an Imperas point of view. Imperas is a small startup. We're self-funded. We get our revenue from customers, and we sell technology. We sell our products. We sell our simulators. We sell our tools. But the RISC-V community, and metrics is the same. Okay. Now, from an Imperas point of view, what we've done is we've looked to the community. We've said this is a very exciting thing. The world is changing. RISC-V is contributing to that change. We want to help somehow. Yes, we want to make money selling tools to big companies doing all sorts of things. And what we've done is we've said, how can we contribute to the community? And what we've done is we've said we've taken a version of our simulator, which we sell, and we've made it free on GitHub in a constrained way. So it does exactly what the RISC-V Foundation does, and we've made it free without, I think there's a click-through to say you're not going to reverse engineer it or whatever, but it's downloadable and usable. And we're working with people like Google to include it in there so that everybody can use it as part of those environments. And because we're trying to help people like the Open Hardware Group, Chips Alliance, to move the cause forward and everything, they need a good reference. We're providing it. So it's not open source. The model actually is open source under an Apache license, but the actual simulator is a closed source binary deliverable, which it can be used for free around the RISC-V community, and that's from an Imperas point of view. So we make it available for free. So it's not open source, but it's freely available on GitHub, and it's actually part of the compliance suite. It's part of the bit manipulation, and it's there on its own. I don't know, Doug, if you want to.
Thank you very much.
And in particular, we're figuring out how to support the open source community sort of in a GitHub-like model where perhaps if your stuff is open source, we would have a free version for that. We're working with some people like Open Hardware and Chips, but still figuring out the details of exactly how that would work, because unlike something like a GitHub, there's a lot of compute behind this, so a real cost, right, to run many hundreds of simulations. So we're trying to figure out how we can support the open source community, and there'll be some announcements of that coming in the future. For right now, it's still a commercial product for the primary part.
I see. And I have a follow-up question. So here it seems the simulation is run on the cloud, and so how do they protect their RTL if they are going to develop some property products?
Oh, okay. I think I understand. Can you hear me? Yes.
Yeah. Yes.
All right. So I did mention that Git is our mechanism for getting your data into the cloud. Yeah. So basically, you commit your code to a Git repository, and it could be either on GitHub, or we can provide an instance of GitLab for you to use. And basically, when you want to use metrics, you just have to push your code to Git. We can clone that, and we can run simulations. Does that make sense? Did that answer your question?
Yes. That means I have to commit our RTL code to the cloud.
Yes, it does.
To your private Git account.
To either a private GitHub account or, in the case of metrics, if you're a corporate user, you get a dedicated set of machines, and without going into a deep discussion of how that's secured, there is a lot of consideration of security, and working with corporate IT team, we can assure you of the details of that. Yeah.
I see. Thank you.
Okay, thank you. Should we go left to right? We should go right this time.
I'm not sure if the formal verification was part of the agenda, but I was just curious if you could talk about formal verification resources available for RISC-V.
Yeah, formal. So, yeah. So I think what we've been talking about is what I'd call a dynamic verification there. And I'll answer the question because I spend a lot of my time in this. So in the RISC-V Foundation, there has been a lot of talk about it, and there's been a formal working group actually since day one, and there's been lots of discussion about how, from a foundation's point of view, how we could have a defined standard of the RISC-V. There has not been a lot of discussion about the technology of verification being formal. So, you know, there's a lot of EDA technologies out there which do formal proofs and things like that. And there is a group, Symbiotic EDA, have technology around the formal side of things. So there are lots of different formal technologies in the standard SoC, RTL development world. The RISC-V Foundation isn't really the only bit informal that it's been focused on is having a model of the ISA in a formal way. And there were 5 or 6 of them that were part of that working group. A choice was made on one. There are no tools today which go from the formal model to RTL and to do the model checking and proving like that. The other 4 or 5 of those formal models of RISC-V do have tool flows around them. And if you look at the RISC-V Foundation, go to the formal bit, there's links to those and there's reports on those. But we're not really involved in that. We're trying to focus on the dynamic side of things. But there are other groups that are getting involved in that or do that. Okay.
Thanks.
What type of report capability does the metrics tool have? And can you handle export controlled code?
To the report question, there's a wide variety of reports. You saw some of the coverage and such that you know, Amy had demoed in the demo there, which is usually a key piece of data that verification teams are looking at.
Let me clarify, reports that can go into documentation for certification purposes.
For certification. Well, all of the data is available to be, you know, extracted and put into whatever forms you need for documentation. There's not a certification standard report output at this time, but you know, all of the core data is available there to put into whatever reporting framework you like. As far as you know, if you're talking about you know, some of the either military or such things where you have to have certain certifications of who's touching the code. Well, I mean, we run on top of Google Cloud, so you know, to the extent that their systems are sufficient, it should pass through because you do get a dedicated cluster of machines with all the standard protections and such there of data. But it really depend on what assurances you'd need. Yeah.
Great. Okay, thanks very much for your questions. So thank you very much for coming along. Obviously, we've been talking about the work we're doing, for verification RISC-V. We're actually setting up a working group related to this to work within the Open Hardware Group and CHIPS Alliance. So if you want to find out or keep track of this, keep an eye on those two organizations, and at some point we'll make an announcement of what we're doing, and you could join those working groups and participate and be kept up to date with it. So thanks very much for coming along. We'll hang around outside if you've got more questions. So thanks very much.